We are back in thermodynamics with class 14. Continuing on, I think we're going to be in section 4.3 of the book Bornacki, and we're going to talk about steady state processes. And this continues on into class 15 and class 16, and then we wrap up the end of the chapter. So we had some discussion where I told a story about being in a D-type boiler. This I couldn't find a really good representation, but when we went into Casablanca, this is the area where we had a ladder in, right? So I was washing down the surfaces of the superheater, which is right in here. So you can see that what the superheater does is we go. I don't need to teach you everything, but this is things to come. This is like practical thermodynamics and what it gets used for a steam plant. And this is a basic one on a ship where we have, it's called an economizer, where we take a pump and we're pumping water. It goes through this, it heats it up a little bit, goes into the water drum. Water steam drum. I guess we usually call it a steam drum. Down here, sometimes they call it a water drum. Also, there's the mud drum down there. And the steam comes out and it goes through the superheater. So it's wet steam when it comes out of here, but it goes through the superheater and gets superheated, and then goes to the turbines, through a condenser, and then through a condensate pump, comes up through a direct contact heater back to a feed pump, and you got yourself a cycle. And you'll be doing this. This is called the Rankine cycle sometimes by some people. Here's a more complicated one. So this is actually off of a ship. I think I took the name of the ship off of here, but this is like a formal thing that we do on ships, and we get all the mass. This right here is just a combination of the conservation of mass and the conservation of energy. And here's a bunch of different heaters where they're doing different stages of heating along the way. And so we're going to talk about a heat exchanger. I think it's going to be in this lesson today. So be on the lookout for that. This is the ship that John likes, where the boiler blew up. I figured you'd see some pictures for context. Here's the ship at the pier. I think this is in Montreal. There's the boss of the engine room, so you can see how grimy this is. This is not a military ship, right? This is a commercial, and an old commercial ship. These style of ships have probably gone away. They were called break bulk. Here's like a third assistant. He's the day third assistant. Here's on a watch standing third assistant. Guys I worked with, and this is me in Somalia having a beverage of sorts on. But so that's actually a different ship than that one. Here's me at the academy. So you can see here's what it looks like when you're at the Merchant Marine Academy, while you're there wearing uniforms. And you had to wear a gym uniform all the time, or here's a boiler suit, and I figured I could go to class in that all the time. Here's a dress blues. But here's out at sea, here's the room that actually it was my sea partner's room on that same ship, I believe, maybe. And then here's me in Egypt. But anyway, I thought it was a funny contrast between here's what it looks like when you're out on ships, and here's what it looks like when you're at Merchant Marine Academy. So that was not necessary at all, but I figured I'd put it in there because I told you the ship about the boiler that blew up on the John Likes in 1989. All right, so we're talking about steady state processes, and I just wasted 3 minutes of your life. But you know what? I don't think you're going to watch this, so I did it anyway. So a steady state process is the one we generally are going to look. So we were talking about transient processes, and talking about sometimes we talk about the accumulation or the deterioration of mass or energy within a control volume. Steady state process, you turn your back, you look back at the thing, and it's the same conditions as before. That doesn't mean things aren't moving. They're just always moving the same amount. So we want to have the model for the long-term steady operation of the devices, and usually made up of things like turbines, compressors, nozzles, boilers, condensers, all of the stuff that I was just talking about right here, these individual components. That's what we're usually taking a look at, right? So using these tools, we have a purpose for them. So the control volume doesn't move. The coordinate frame of so the velocities are absolute velocities, and there are no relative velocities, and there's no accelerations really associated with the control volume. The state of the mass at each point of the control volume doesn't vary with time. This implies that the left-hand side of the continuity equation is 0. right? Well, and the energy equations, both the continuity equation and the energy equations. Usually the stuff on the left-hand side is the stuff about accumulating or deteriorating, and it stays the same. And so this right there, that's the equations that state that. And the flow, the flow rate and the state of the masses as it moves across the control surface do not vary, right? So things can enter and leave the control volume, but the rate at which they do stays steady. And that includes also the heat and work also crossing the control surface remain constant. So do I want to switch over, or is this okay? No, I don't. We're good. All right, so there's the continuity equation at the top, and here's the energy equation. And personally, I think this may be the point at which we want to take a quick thing and go, here's the equation we're going to use almost all the time for when it comes to conservation of mass. And here's the equation we're going to use almost all the time for conservation of energy. And we're going to use it over and over and over again. Here's just saying that, like, a lot of times if it's just one mass, you have the mass flow coming in is equal to the mass flow going out. And sometimes we'll just call that mass flow because it's the same, so we don't bother. We might rearrange this up here and expand this total enthalpy in and the total enthalpy exiting into the enthalpy coming in, right, and the kinetic energy coming in, and then this is like the potential energy coming in, and these are all per mass right here. And what we will see, we're going to make sure we're on the lookout for that these guys right here are usually, at least for the stuff that we do, they're usually really small compared to this, right? And there's already a little bit of kinetic energy involved with the enthalpy, but yeah, so sometimes it's just on a whatever our situation basis is, but most of the time we'll be dealing with this equation up here, and what they're mentioning, they're kind of breaking this total down into there. So rearranging this equation right here, though, we can, on a per mass basis, right? So this is, we can divide all the way through by m dot everywhere, right? And so we do that's our per mass basis type of thing. But you'll notice that the work now becomes a lowercase w, and also the heat becomes a lowercase q right in there. So that's a good equation to use a lot of times, because we can actually calculate a lot, learn a lot about a cycle without knowing how much mass is flowing through it. We can actually get, in many instances, we will get the efficiency, and we'll find out from the cycle using this concept right here, the per mass basis. So it's very common to do. So I'm going to now close this down, and we will have the next video will be this example.